Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, wood stoves. The purpose of a wood stove is to heat a room with heat released by burning wood. And in contrast to an open fire or even a fireplace, a wood stove confines the burning process so that you get the heat in the room, but not the smoke. Well, to understand how a wood stove works and how it conveys heat into the room, even what heat is, let's start at the beginning with thermal energy. Thermal energy is ordinary energy, that is, it's kinetic energy, potential energy, but in contrast to the ordered forms of energy, the forms that are capable of doing work and a physicist would describe as equivalent to work, thermal energy is lots of little pieces of energy sliced up and distributed statistically among all the particles that make up an object or a situation. And because that energy is so diced up and distributed statistically, it's very hard to do things with it. It can't simply do work. All right? You can turn ordered energy into thermal energy fairly easily. That is, breaking up the energy is easy. Putting it back together, again, much harder. So the thermal energy that will come out of the wood stove in the process of heating the room starts as energy, in fact it's ordered energy, and it's sort of degrading, it's working its way into this thermal statistical world. And we can follow that energy from its origin, which is as chemical potential energy in the wood and also in the air in the form of oxygen. And so there's something that goes on between wood and oxygen that converts stored energy, chemical potential energy, into thermal energy. And once there is thermal energy present, initially it's present in the burning wood and in the gases coming off the burning wood, and then it works its way out into the room. And when thermal energy moves from one object or one place to another, physicists describe this as the flow of energy as heat. So just to pin this down a little carefully, let me go back to the idea of energy and work. If you remember, energy is something that you have. You can have a certain amount of energy, somebody else can have a certain amount of energy. If you convey energy to someone else in an orderly fashion, you do it by work. You do work on something. You convey your energy to it by exerting force on it as it moves a distance in the direction of that force. Good old-fashioned work. In the world of thermal energy, energy can move from one object to another, and as we'll see, it moves always from hotter objects to colder objects if you're allowed to just go on its own. When it moves as heat. So the transfer of thermal energy from one object to another is the flow of heat. So just to step back sort of for the moment, there turn out to be two ways to convey energy to something. You can do work on it, and that's the mechanical means of transferring energy. And you can pass heat to it, which is the thermal way of transferring energy to something. So that we're broadening our view of the mechanisms for transferring energy to include the transfer of thermal energy as heat. And the purists will say that an object does not contain heat, it contains thermal energy. It's when the heat moves from one object to another that it moves as heat. Okay. That said, where does the thermal energy sort of come from in the burning wood? It turns out that it comes from chemical reactions that occur between the molecules that make up the wood and the molecules that are present in the air, oxygen molecules. And the idea starts as this, that whenever you have two atoms at great distance from one another, they could care less about each other. They're far enough apart, they don't care. But as you bring them closer together, and suppose you have little tweezers and you grab them and you slowly bring them toward each other, at modest distances, that is not large like this, but when they start to get reasonably close, they will attract one another. The forces between two atoms at some distance from one another are always attractive. So they start attractive, and as the atoms get closer and closer to one another, the attraction eventually starts getting weaker until finally it reaches zero. And then if they get even closer still, it goes the other way. It becomes repulsive. So there's an attractive force at large distances. It gets stronger for a while, then it starts getting weaker, and then it goes the other way and becomes repulsive, pushing them apart. And if you gradually bring the atoms in together and let them reach that point where they neither attract nor repel, there is a special point at which they exert no force on each other, that's equilibrium. And they can sit at equilibrium, and if you let go, they will stay at equilibrium in principle sort of indefinitely. They're happy. And if you want to take them apart, you have to pull, because as you start to separate them, they attract again. And you have to do work to pull them apart. So they're held together by a deficit of energy. In fact, as you first brought them together, they did work on you while they were attracting each other at great, significant distances. And when you got to equilibrium, that's the point at which they had done maximum work on you. If you went any closer, you'd have to shove them together, and you'd have to do work on them. So you bring them in, they did work on you, and then you let go, they're stuck. They can't come apart unless something pays back that missing energy, the energy that was given to you. So that deficit of energy is the origin of the chemical bond. The fact that they did work on you coming as they came together, and you walked away with their energy, they're stuck. They're chemically bonded to one another. That said, different atoms and different collections of atoms will attract to different extents. And so it's possible to take some group of atoms, bring them together in a certain arrangement, and have them do a certain amount of work on you, and therefore be bound together by a certain deficit of energy. And yet there is another arrangement of those same atoms assembled that would have developed a larger deficit of energy, stronger chemical bonds, and would have done more work on you. So if you bring them together in the first arrangement, and they do a certain amount of work, and then you come back and you rearrange them in a new way, they would do more work on you. And that means that you can have atoms and molecules that are assembled in one way that still have chemical potential energy. They can still release more energy by rearranging, undergoing reactions. And if you let them work their way to the new place, hey, it's great, they've released extra energy. And that's what happens in the wood stove, is the wood stove has molecules and stuff all assembled before you even light the fire. Once you get the fire going, those molecules, which, they're assembled by way of chemical bonds in various ways, but they can rearrange. And in doing so, they will release still more energy. Not necessarily to you, but to somewhere, and they will form new molecules that have stronger chemical bonds overall. They have a net larger deficit of energy in this new arrangement. And so what are those molecules essentially? Well, first of all, there's oxygen in the air, and oxygen in the air is actually two oxygen atoms stuck together. You will not find oxygen atoms on their own, they always pair up. So the oxygen atoms were already stuck to each other, released some energy, but they still can do better. Okay? And in the wood, mostly you have cellulose, which is based on sugars. Actually, it's a sugar polymer. It's basically the most abundant plastic in the world. Cellulose is a sugar polymer. It's giant molecules built of sugar pieces, and they are chemically bonded together. But you can rearrange them and release more energy. And when the two get together, the cellulose molecules that are the dominant thing in wood, and the oxygen molecules in the air, and they rearrange and they form new molecules. Those new molecules can have tighter chemical bonds and lower total chemical potential energy, a bigger deficit, in fact, of energy. So energy was released in this rearrangement. The new molecules that form are primarily water molecules and carbon dioxide molecules. So wood, for all practical purposes, wood and oxygen burn together to form water and carbon dioxide. There's other stuff around. Obviously, smoke is not as you don't want to breathe smoke, not because it has water and carbon dioxide in it, but because of all the other junk that's in there too. All right, so allowing these molecules to rearrange can release energy. One thing to point out, though, is the rearrangement doesn't happen easily. that is a piece of wood sitting there and a oxygen molecule sitting there, coming into contact. They can do that all day and not much happens. To get the rearrangement going, you have to sort of pry apart the molecules a bit, enough so that they can figure out how to rearrange. And so there's an initial investment of energy that has to go into those molecules to get them started in doing the reaction. And that initial investment of energy is known as an activation energy, to get them sort of over the hump to begin the rearrangement. And that's why you have to light the fire. The energy that you're bringing in initially, the high temperatures and stuff, allows for the transformation of the original collection of molecules, or the reactants, into the reaction products. So you have to light fires. There are chemical reactions that occur spontaneously at room temperature, and there are ones that happen, in fact, at any temperature. But this is not a case of that. That you do need to sort of get everything going, knock it, to jostle the molecules apart so that they can find the new way to rearrange and release energy. In this case, the energy that's released does come out as thermal energy. So you start with room temperature, say, wood and oxygen, they get together. When they rearrange, the released energy shows up as elevated temperature in the reaction products. It's hot water. In fact, water as a gas, water vapor, and hot carbon dioxide. And you now have created a very hot resulting collection of atoms and molecules. Okay, so that's the burning process inside the wood stove. The chemical reaction releasing what was originally chemical potential energy, ordered energy, and now becomes thermal energy. It's just shattered into tiny pieces, sprinkled everywhere, and the temperature of this stuff goes way up. It's way above room temperature now. So as a result of the difference in temperature you now have between the hot burn products inside the wood stove and the cool room, when you have a temperature difference like that, heat will naturally flow from the hotter place, the higher temperature, to the colder place, the lower temperature. If the temperatures were the same, heat will not flow spontaneously between the two places. So that's an observation about heat. Heat always flows from hotter to colder, from higher temperature to lower temperature. And if the two things are at the same temperature, a situation known as thermal equilibrium, no heat flows. So we'll look more into that when we start looking at the laws of thermodynamics, but those are in our future. All right, so you've got a hot place chock full of extra thermal energy. The temperature's high, the room temperature's low. Heat can flow from hot to cold. How does it actually do this? Well, it uses the three famous mechanisms for heat transfer. There really are three dominant mechanisms, and I can't even think of any other ones. The first one is conduction, which is the passage of heat from hotter to colder through a material without the material itself moving. So heat will be conducted, for example, through metals. Second mechanism for heat to go from one place from hotter to colder is convection, which is heat moving in the movement of a fluid. So you heat a fluid up, you transfer the fluid somewhere else, and with it goes the heat. With it goes the thermal energy in moving with the fluid is heat. And the third mechanism, the more mysterious of the bunch, for transferring heat from hotter to colder is radiation, or thermal radiation. It's the flow of heat from hotter to colder by way of electromagnetic waves. Basically, light and light's relatives. So we'll get to that one at the end, but let's start with heat flowing from hotter to colder by way of conduction. And this occurs in a wood stove between the inside of the stove where the stuff's burning and the outside of the stove where the room area is. One of the features of the wood stove that distinguishes it from an open fire or even a fireplace is that you're not able to touch the burning wood. The burning wood's confined inside this box, and it's the chemicals that are produced in the burning process go up a chimney and out into the outside air. But the heat manages to get into the room. And the first step in getting the heat out of the box and into close to the room air, is to be conducted through the walls of the wood stove. So the wood stove is made of some material, typically a metal, and the heat moves through the metal to get to the outside. And that flow of heat through the metal is heat being conducted. So the mechanism involved is conduction. And thermal conduction starts with the simplest piece of thermal conduction is the movement of heat by way of jostling of adjacent atoms and molecules within a material. So imagine you've got a long, let's look at the wall of the wood stove. Let's slice a chunk, actually a cylinder out of the middle of it, from the hot end where the wood is burning to the cold end where the room air is. So we've got a cylinder of wood stove material. And if we zoom in close enough, you see atoms and molecules. Wow, there they are. And at the hot end, which is essentially in contact with the burning wood, the little atoms and molecules are jostling around wildly because they got lots of thermal energy, which means the average kinetic energy per particle is huge. Okay, so they're jiggling around like crazy and they're bumping into each other. They're not going anywhere overall, but they're jostling fiercely. At the other end, on the other hand, it's cool, it's the room air, and maybe it's a cold day. So the jostling is much more gentle. Well, if you just look at the statistics of this jostling motion up here, it's going to bump into the atoms and molecules adjacent to it, which are going to bump into those next to it, and so all the way across through the metal. And so this jostling motion, the thermal energy here, will tend to statistically work its way through the material to the cold end. In principle, it can go the other way. The jostling over here can actually convey energy bit by bit, actually by tiny doses of work across the wrong way. But statistically, that never happens. So the movement of heat from hot to cold is driven by statistics. It's just more likely to go from the place that's chock full of energy and lots of jostling to the place that's not got a lot of energy and relatively gentle jostling. So migrate away it does. And that migration through the material depends on the thickness of the material, how far it's got to go from hot to cold, and what else? On how big the temperatures are between the two. If they're very close in temperature, the jostling statistics don't favor a lot of movement. If the temperatures are hugely different, the heat goes roaring through. So the heat flow is roughly proportional to the separation. It's roughly proportional to the temperature difference. And the last thing that's important in this is the thermal conductivity of the material itself. Some materials convey heat better than others by way of this jostling motion. So they're not all equivalent. Now that's not quite the whole story. In some materials, this bumping and jostling locally isn't the whole story. There are materials in which there's something else that can move through the materials and can convey heat long distances in sort of a single step. And those somethings that can move are electrons or charged particles, the charged particles that are mobile and are associated with metals. So materials that can conduct electricity, which they do by allowing charges to move through them, they can also conduct heat by an extra mechanism, the movement of charged particles. Really, electrons is the one we've got in mind here. So if you have a material that doesn't allow electrons to move around, what's known as an insulator, so something like glass or crystals, actually pick the crystals, a piece of quartz, piece of wood. If you use something that's insulating, ceramics, then the only mechanism for heat transfer is this jostling motion. For materials that can conduct electricity, particularly the metals, copper, aluminum, steel, iron, then the other thing that can carry heat is electrons that zip long distances through the material. They're capable of carrying electricity, they're also capable of carrying heat. And because they can travel long distances through the material before they sort of bump into something and then jostle and fly across and then bump into something, fly across, because of that, their long distance movement, they carry heat very well and they become dominant in metals. They're the biggest contributor to the thermal conductivity of most metals is those electrons zipping around. And that means that metals carry heat better than insulators, with rare exceptions. There's some oddball things around, but basically metals are generally good conductors, and insulators are generally bad conductors, where insulators are reference to electrical conductivity. So using metal walls on a wood stove facilitates the movement of heat from the inside of the wood stove where the fire is to the outside of the wood stove where the air is. So that's the world of thermal conductivity. Thermal conductivity shows up in many things, sort of in everything, but it's not necessarily important in them. For example, air is a terrible thermal conductor of heat. That is, if you can keep the air from moving, which is a tricky thing, we'll see in a minute, if you can just keep the air frozen in place and you put hot over here and cold over there, the heat tries to conduct through the air. It's really slow. It's really terrible conductor. So I mean, the difference between that and a chunk of copper, woohoo, huge difference in thermal conductivity. All right, so the wood stove is made of a material that can conduct heat reasonably well. Now the temperature, therefore, of the outside of the wood stove gets good and hot. And now it's the time for the heat to flow into the room. How does it do it? Well, it doesn't do it by thermal conductivity. The air is a crummy conductor of heat, as I just said. So what else is there? Well, the first possibility, there are two, I'm going to get to the second one later. The first possibility is convection. And what convection is the heating of a fluid and the migration of that fluid, the movement of that fluid. And in this case, air. So air is a terrible conductor of heat, but you can heat it locally near the surface of the wood stove and then have the air move. And air will tend to do this spontaneously, because when you heat air up, and in an environment that's all at atmospheric pressure, when you heat air up, in order for it to maintain atmospheric pressure, it has to reduce in density. If the air simply heated up and at the same density, its pressure would increase, and it will accelerate away sort of from where it was, spread out. So the air near the wood stove rises in temperature and decreases in density. When that happens, when its density goes down, it becomes buoyant in the surrounding air. The surrounding air was used to supporting it when it was at normal atmospheric density. But because it's now hot and its density is low, it's over-supported and it rises. Hot air rises, up it goes. So the air around the wood stove is lifted by buoyant forces that exceed its own weight and send it up toward the ceiling. Up it goes, whoosh. And once it gets to the ceiling, it cools off, or spreads out eventually. It cools off and then it descends. And you get what are called convection cells, where air is rising off the wood stove, and off it goes, and to replace it, cooler air is coming in from below, and it cycles around the room over and over again. And this carries heat up to the ceiling and spreads it around the room, and to some extent it heats the rest of the room, but it's not perfect. It would be great if we lived up there near the ceiling. Most of us live down here on the floor, and therefore you kind of want that air to come down here where it's better. So instead of just using natural convection, which is the convection associated with the natural buoyancy of air when you heat it, it helps to go to forced convection. Propel the air around deliberately. Use a fan. So if you put a ceiling fan up near or above the wood stove, as the air rises up into the ceiling fan, it blows it around the room and sort of homogenizes the temperature. So you get a uniform temperature in the room instead of hot in the ceiling and cold down here where we live. And so wood stoves and ceiling fans work together very nicely. Okay, so that's a way of conveying heat into the room, from the hotter surface of the wood stove to the cooler room air and the rest of the room. What about the third, and as I say, somewhat mysterious mechanism for heat transfer? That's thermal radiation. And it's the emission of electromagnetic waves such as light. What we see as light is a small portion of the possibilities of electromagnetic waves. So the electromagnetic waves are distinguished by certain characteristics, which can be thought of as frequency or wavelength. The two are directly related, so you pick one or the other, doesn't make a big difference. But the idea is this: the electromagnetic spectrum it includes, or things that are electromagnetic phenomena includes, radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. It's a whole spectrum that is distinguished by wavelength is one possibility, from long wavelength radio waves to very short wavelength gamma rays, or we can do it by way of frequency, in which case it's low frequency for radio waves all the way up to very high frequency for gamma rays. The point here, though, is that these electromagnetic waves, which work their way through empty space at approximately the speed of light, the famous speed of light, those electromagnetic waves, they carry interesting information, radio waves and with light, whatever. They can also carry thermal energy. They carry energy in general. In this case, they're going to carry thermal energy. They'll move heat from hotter to colder. And the electromagnetic waves come off of the wood stove and also off of everything else in the room. Those waves are pretty much all in the end of the spectrum that doesn't quite reach up to visible light. So they cover the radio waves all the way up to the infrared, but they don't quite get to visible light. At very high temperatures, like if you open the wood stove and look inside and see the quite high temperatures of the burning wood, the thermal energy that's being radiated away from that burning wood includes the visible, particularly the red end of the rainbow spectrum, and up into maybe a little bit of the oranges and yellows and maybe greens. Okay? Close the door again. Now, the wood stove doesn't appear to be emitting anything. You can't see it with your eyes. Is it really there? Well, yeah, you can feel it with your hands and with your face. You feel something coming at you. And even if you don't you turn off the ceiling fan, let the hot air rise off the wood stove, so you're not in that hot air. If you put your hand in it, you can feel that heat, the hot air rising. But go away from that. No, you're not in the rising hot air. You are not touching the wood stove, so there's not much conduction. You're not in the hot air, so you're not getting much convection, and yet you feel warm. Your face feels warm. And actually, if you put your hand in front of your face, it cools off. You're blocking something. You're blocking thermal radiation. You can't see it with your eyes, but it's there. It's primarily infrared light. It's light that our eyes are not sensitive to it, but other things. There are devices that observe it. But we only perceive it as the flow of heat. And so the wood stove is radiating away thermal energy quite brightly, and we are actually also radiating thermal energy. Everything in the room is radiating thermal energy, but the amount and the wavelength characteristics of the thermal energy that any surface emits depend on its temperature. And the cooler the surface is, the less bright the thermal radiation is, and the longer in wavelength, the more towards the radio wave end of the spectrum that thermal radiation goes. So there's actually an exchange of thermal radiation between you and the wood stove when you stand back and look at it, and you feel the heat coming at you by way of radiation. But it's actually an exchange. The wood stove sending thermal radiation at you, you're sending thermal radiation at the wood stove. However, its thermal radiation is a lot brighter than yours. So in that exchange, it wins. It sends more to you than you send back to it by a lot. And the result is there's a net flow of thermal radiation, of heat to you. And so the wood stove, heated by the wood burning inside, with heat conducted to the surfaces, it's glowing. It's radiating away thermal energy to everything in the room. And so apart from this convection behavior, heat flowing by convection out around the room, there's this general glow that heats everything. And as long as if you can see the wood stove, that means there's a direct line of sight between you and the wood stove. It's sending, among other things, it's sending thermal radiation right at you. You can feel it, typically. So that's most of the story of the wood stove heating the room. One last thing to put in there is so how much thermal energy has to come out as heat out of the wood stove to heat the room up. And that depends on a characteristic of all the materials in the room, known as their heat capacity. basically how much thermal energy do you have to put into a certain amount of an object to raise its temperature 1 degree, 10 degrees, 100 degrees. Different things have different heat capacities, which is to say it takes more heat to raise the temperature of one object than it does to raise the temperature of the other. This is typically reduced down to the specific heat, the energy it takes to heat each gram, for example, of a certain material. Water, it turns out, it requires quite a large amount of thermal energy to raise its temperature 1 degree Celsius, to pick a set of units. Whereas some of the metals are pretty easy to heat up. They don't have the same specific heat. Much smaller. It takes less thermal energy to heat a gram of a typical metal than it does to heat a gram of water of the same temperature increase. Get the same temperature increase. All right, so some of the things in the room are very slow to heat up. A big bucket of water off in the corner, it's going to stay cool for a long time because it needs a lot of thermal energy before its temperature will budge much. Some of the other parts of the room, they'll heat up quickly. With that said, then, I'm going to call it a day. I've looked at wood stoves. They release thermal energy by burning wood in oxygen. That chemical reaction and rearrangement results in molecules that are more tightly attached to one another, that have stronger chemical bonds, bigger deficit of chemical potential energy. The energy that was released to form those new molecules comes out as thermal energy. You get real hot stuff inside the wood stove, and the thermal energy there works its way out into the room as heat from hotter to colder by the three mechanisms of heat transfer. Conduction, particularly through the walls of the wood stove, convection around in the air surrounding the wood stove and in the room, and finally thermal radiation coming off the surface of the wood stove and flying straight and true to everything else in the room. There's an exchange back and forth, but the wood stove wins. It's the hottest thing in the room, so thermal radiation from it moves, overwhelms thermal radiation from the room to the wood stove, and you get a net flow of heat from the wood stove to the room by way of thermal radiation. And that's the story of wood stoves.